Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 8 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. This is the problem I'm going to be tackling today. We have a positive integer n and we let s be a set such that for all a in s, so for all elements a in s, a is actually a subset of the set 1, 2, all the way up to n. So essentially s is a set of sets. So S is a set of subsets of the set 1, 2, 3, all the way up to n. And if we take an element A in S, then it must obviously be a subset of the set 1 up to n, but also we must have the cardinality of A, so the number of elements in A is 3, and also for any B in S, so for any other set in S with A and B distinct, we must have that their intersection, they intersect at most at one point. So if you do the cardinality of A intersect B, you're either going to get 0 or 1. We want to let f of n denote the maximum size of s, and we want to prove this inequality here holds. That n minus 1 times n minus 2 divided by 6 is less than or equal to f of n, and f of n is also less than or equal to n times n minus 1 over 6. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing I'm going to do is prove our upper bound, and that is that f of n is at most n times n minus 1 over 6. And the way we're going to prove this is firstly by starting off with our set S and just labelling its elements. So I'm going to call them A1, A2, and so on all the way up to AK, like so. And then we know from the statement of the problem that each of the AIs are going to be subsets of 1, 2, all the way up to n. And we also have that the cardinality of each of these AIs is just 3. The next thing I want to do is consider the set of subsets of the set 1 up to n of size 2, and those subsets must be a subset of one of these guys here. So let me write out what I mean by that. So U is going to be defined to be equal to the set of B, which are going to be subsets of 1, 2, all the way up to n, with the cardinality of B being equal to 2, and B must be a subset of AI for some I. Okay, so essentially we're looking at pairs from the set 1, 2, all the way up to n, which kind of occur in one of these sets here. So, for example, if A1 was, just say 1, 2, 3, then we'd have, in this guy here, we'd have the guys 1, 2, 1, 3, and 2, 3, because all of these guys here are from the set 1 up to n. They all have cardinality 2, and they're all a subset of one of these AIs, namely A1, like so. So we have this guy, this set U, but also what we want to notice is that for each element in this guy here, it corresponds to an element in S, and that the element it corresponds to is unique. And how am I kind of getting this correspondence? Well, I'm taking an element from here, and let's say let's just keep it generic, ABC. So that's, AB, and that's going to be in U. And then because this guy here, from this property here, must be a subset of AI for some AI, that's the set in S I'm going to correspond it to. So let's suppose that this guy here, suppose that AB is a subset of, say, AI for some I, and I claim that that I is unique. So in other words, AB is never going to be a subset of AJ, where J is distinct from I. Well, because if AB was a subset of AJ for J not equal to I, well then that implies that the cardinality of AI intersects AJ would be 2. Okay, but that contradicts, one of the properties of S. So this is not possible. So in other words, if we take any element in this guy here, in U, that corresponds to a unique element in S. But notice that we can kind of, if you think about this a bit better, we can see this relationship actually has kind of a three-way thing going on. So we can take 3 elements from this guy here, and that will correspond to a unique element in S. So if we take the element in S, just take one of the AIs in here, this guy, let's call it alpha, beta, and gamma, then we know that that guy there corresponds to 3 sets in this guy here, namely alpha, beta, alpha, gamma, and beta, gamma, like so. So we take 3 guys from this guy here, and that corresponds to one thing here. So in other words, we have that 3 times the cardinality of S is equal to the cardinality of U, like so. From this kind of 3 things in here correspond to 1 thing in here, so the size of this guy here must be 3 times the size of this guy here, so 3 times S is equal to U. But then we can find a bound on U pretty clearly, because U is a subset of the sets, U is a subset of the set of subsets of this guy here of size 2. So U is a subset of the set of B, which are subsets of 1, 2, all the way up to n, where the cardinality of B is just 2. But this is another way of seeing the cardinality of this guy here is simply n choose 2, because it's a number of ways of choosing 2 elements from the set 1 up to n. So because U is a subset of this set, that means that the cardinality of U must be less than or equal to n choose 2. So we get that the cardinality of U is less than or equal to n choose 2, but n choose 2 is simply n times n minus 1 over 2. Plugging that into here, we get this thing here is less than or equal to n times n minus 1 over 2, and then dividing both sides by 3 is going to give us S is less than or equal to n times n minus 1 over 6, which is exactly what we claimed. So that proves the upper bound part. Let me clean up the whiteboard and we'll move on to the lower bound. Okay, so now I claim that f of n is at least n minus 1 times n minus 2 over 6. And the way we're going to do this is by recalling what f of n is. F of n is the maximum possible size that S could be. So if we can show that there exists a valid S, which has size at least n minus 1, n minus 2 over 6, then that will of course imply that f of n is at least n minus 1 times n minus 2 over 6. So what we're going to do is generate n of these sets S and show that at least one of them must have size n minus 1 times n minus 2 over 6, and then we'll be done. So what are these sets? Well, I'm going to define for j in the sets 0, 1, all the way up to n minus 1, I'm going to consider the set Sj, which is going to be this set of triples ABC, which are going to be subsets of 1, 2, all the way up to n, with the property that A plus B plus C is congruent to J mod n, like so. So this is what I'm defining Sj to be for j between 0 and n minus 1, so there are clearly n of these Sj's. And firstly, we need to check that Sj satisfies the properties to be a valid S. Firstly, it's a set of subsets of the set 1 to 2 up to n. That's pretty clear. Secondly, each element has cardinality 3, and again, that's pretty clear because they're all of the form ABC. And the final thing we need to check is that if we take any 2 distinct elements in S, look at their intersection, then the cardinality of that will be less than or equal to 1. So either 0 or 1. Well, to see that, firstly notice that if we take any 2 elements in S, because they're both cardinality 3, when we look at their intersection, that's going to either be 0, 1, 2, or 3. But because we're considering 2 distinct ones, then the cardinality of their intersection can't be 3. So that means it's either 0, 1, or 2, and we want to show that it's either 0 or 1, so that essentially is the same as proving that it's not 2. So what we're going to do is suppose for contradiction there exists 2 distinct elements in Sj whose intersection has cardinality 2. So then that means that those 2 elements are of the form ABC and A, B, and say C tilde, where C and C tilde are distinct. So of course the 2 intersecting elements are A and B. Anyway, what we now notice is if we just look back to our definition of Sj, we must have that A plus B plus C is congruent to A plus B plus C tilde, which will be congruent to J mod n. Well, then just cancelling A plus B on both sides, we get that C is congruent to C tilde mod n. But remember, C and C tilde are in the set 1, 2, all the way up to n, so that means if they have the same residue mod n, that must mean they are the same number. So this would then imply that C equals C tilde, which is a contradiction because we're assuming that these 2 sets here are distinct. So that means that Sj can't have 2 distinct sets whose intersection have cardinality 2, so that means that each of the Sj's do in fact satisfy the properties that we need S to have. So now that we have this, what I want to do, or what I claim, is that at least one of these Sj's will have cardinality n minus 1 times n minus 2 over 6. And the way we're going to do that is just by considering the sum of their cardinality, so the sum from j equals 0 to n minus 1 of the cardinalities of Sj. Now, we don't know really what the cardinality of each of the Sj's are individually, but what we do know is this guy here, which is quite cool, because this guy here is simply the sum of all the cardinalities of all the Sj's, But if we think about it, all the SJs are simply the number of triples from the set 1, 2, all the way up to n. Because if you take any triple from the set 1, 2, 3, all the way up to n, then when you add up each three of those numbers and look at that result mod n, you are going to get a number between 0 and n minus 1. So it's going to correspond to one of these SJs. So when you add this up, that's the same thing as counting the number of triples from the subset 1, 2, all the way up to n, which of course is just n choose 3. But n choose 3 is just n times n minus 1 times n minus 2 all over 3 factorial, which is just 6. So we have the sum from j equals 0 to n minus 1 of sj is equal to n times n minus 1 times n minus 2 over 6. But because we're summing up n elements here, and we're getting this thing here, that means at least one of these guys here, so in other words, there exists j such that sj is bigger than or equal to n minus 1 times n minus 2 all over 6. And this kind of comes from a pigeonhole principle kind of argument, but essentially if this wasn't the case, then we'd have that each of these SJs here have cardinality strictly less than this thing here. So then when we add them up, this guy here is going to be strictly less than n times this guy here, but that's impossible because we've shown that the sum is exactly equal to that guy there, so it can't be strictly less than that thing there. So that means this guy here is indeed true. There exists Sj such that the cardinality of Sj is bigger than or equal to this thing here. So of course then that implies that f of n is bigger than that guy there. So n minus 1 times n minus 2 all over 6, which is exactly what we claim. So that proves that part. Then combining the first part and the second part gives us this kind of sandwiching bound on f of n. Anyway, I hope that has all made sense, and thank you for watching. I'll catch you in the next one. Have a great day.